edition of POS Day celebration by IEEE Power and Energy Society Young Professional. Today we will be exploring microgrids. My name is Donya Memi and I am happy to be your host today. I am the POS Day liaison within IEEE POS Young Professional Committee. And I am honored to welcome to this webinar today Mr. Mohamed Sief. Before that, we have with us Mr. Albin Paul, and he will introduce POS Young Professional activity. So, Mr. Albin, you can start.
Hi, Donia, and hi, Sief. Thank you very much. First of all, I would like to wish happy Earth Day. On this day, we celebrate the Earth Day, and it's very privilege for the PES and professional to host the PES Day event on this particular day and to be part of the great PES Day celebration. So I would like to first of all, I would like to introduce or say a few words about the PES and professional. As you all know, in the IEEE membership grade, after the student membership, the next stage is the young professional membership. So the young professionals are those who are after the first degree, graduation degree up to 15 years, they will be considered as the young professionals. So we are PES and professional. We were working with the Power and Energy Society, and we are focused to provide more technical knowledge, more industry connection, and mentoring to the young professionals and the final year students who will step up into the professional level. So in this year, we have a great team with various subcommittees to ensure that we will provide the membership value enhancement program to all the states. So we have the technical activity coordination committee, we have professional activities and education, professional and educational activity subcommittee, and we have industry connection and entrepreneurship subcommittee and like that. So the dedicated PES volunteers were leading these subcommittees. And also we have the regional representative to ensure our program visibility across all chapters and to get support the young professional member across all parts of the web. So we have a regional representative for USA, Canada, and EMEA region and Asia Pacific region, and also for the Latin American region. So I encourage the PES and professionals who were watching this episode to register as a chapter representative of PES and professionals so that you can represent your chapter in the PES YP Global Committee, and also you can be part of this team and learn from our team members, and I'm sure that it will be definitely helpful for you. So we had various events like the Powering the Future Summit and Meet NYP funding and various initiatives. So we will share more updates about the PSYP through our social media platform and social media channel. So I encourage you to follow PSYP social media channel. Then it will help you to get updates about the PES and professional. So that's all about, that's just brief about the PES and professional. So I don't take much time. I know you are eagerly waiting to hear from our distinguished speaker. So I wish to hand over the section to him. So Sonia.
Thanks, Mr. Albin, for this introduction. And now I would like to welcome again Mr. Saif.
Yes, thanks very much. I really wish you have a nice day. I think I need to.
Thank you.
I need to start with presenting myself. My name is Mohamed Sief, electrical power engineer. I'm working in this field for more than 10 years in the high voltage substations especially, and I have some experience in the solar energy and microgrids during my studies. And today we are going to share this knowledge. Especially, I got it from IEEE PES magazine. Uh, Later, I will let you know more how to get such um, material online from the IEEE PES Resource Center. And let's start sharing the slides. 1 second. Here is, I think it's here. I want to share my screen. Yes, I think it's ready now, right? Okay, so I hope my voice is clear. Everything is okay.
Yeah,
So,
no problem.
yeah, yes. So today we are going to talk about microgrids. From its name, it's something micro. So the grid is connection of generation and loads. Okay, so let's simplify it. We will have small generations and small loads. Okay, sometimes they could be connected to the main grid or disconnected. If they are connected, it will be normally connected to the grid as a from its name, and if they are disconnected, they called it islanded mode, like an island in the sea or in the ocean. Okay, so let's get started. In the first place, why we need microgrids? That's very important in order to decide if we need to choose to have microgrid in our city or not. We need to check in first place why we need microgrid. Mainly, we need it for environmental and economical benefit in order to reduce the CO2 emissions. As we can see here, accordingly, the annual CO2 emission could reduced by 5% by 2030, according to the, you can say, um, yeah, statistics by the US Power System Generation. So we can have this as a target. If there is a government looking forward to reduce the CO2 emissions for these reasons, it will be really a good choice to start have microgrids in their country. And also we need to manage our future power demands and to make it versatile and informative. Of course, informative means it will be smart grid. It has smart meters. It has sensors in every element in the grid, especially in the level of low voltage, we can say. Low voltage means the grid nearby the load or nearby the customer. Low voltage could have different definitions in some standards, but it could be, in general, we can say any voltage lower than 1 kilovolt could considered as low voltage. Okay, also the microgrid is really emerging and becoming more attractive, and the main constituent with the integration RES, which means renewable energy sources. Renewable energy sources like we can say um, solar panels on the rooftops, diesel generators as a backup, um, also the battery systems. Okay, here as you see this terminology, if you would like to write it down, it will be nice, or Google it later. RES, renewable energy source, and DG, this is the diesel generator. ESS is the energy storage system, which means the batteries. Here we can see the concept of the microgrids and topology. What is microgrid as elements? Microgrids can be divided into two main uh, types, we can say. AC microgrid and DC microgrid. And microgrid operation really needs the inverter as a vital part in it. Very important in order to connect it with the grid in any way. As you see here, these green blocks are AC-DC converter, DC-DC converter. Mainly, we use it everywhere, here and here. Okay, so the inverter is an important element which might be interfaced between the DG units, loads, and utility grids in every element. Also, the parallel operation of the inverters in microgrid is enhancing the performance of the system to increase the reliability of this system. If we have any failure in one of the inverters, we could rely on the others. Of course, I don't mean here they are parallel. No, no. Parallel inverters could be here, but two inverters to let us connect the wind turbine to the DC bus. That's what I mean with parallel inverters. Every source could really have a parallel inverter or single inverter. Okay, let's start with the DC microgrid, which really very important, especially in the marine applications, automotive, and the manufacturing industries, especially which needs DC supply. As you see here, the DC microgrid have the that's the source. As we said at the beginning, any microgrid contains source and the loads. Here we have these sources, solar panels, wind turbines, energy storage systems, and the loads. We have DC loads and also AC loads, and maybe we could connect it to the main grid. Okay, the main grid here should be also DC grid. Okay, this grid could be for a marine, for any application like this. So the solar panel and wind turbine, the storage system, and the grid are connected to the DC bus through the converter, and the solar panels are connected through DC-DC converter. The wind turbine, as you see, connected through AC-DC converter. The battery is connected through DC-DC converter. Of course, we know the AC-DC converter is very important in order to convert the power from AC form to DC form. And here, the DC-DC converter is very important in order to regulate the voltage level of the battery system or the solar panels and transfer the power, which is DC, but we can control its values. The DC microgrid very important and increase the electric lines capacity because it will add much amount of energy to the grid. So it will reduce the power loss and the voltage drop. Also, as information, the low voltage DC link in the DC microgrid, I mean the DC link, which means like a connection or cable, is simply supported by bipolar operation. Here we can know what I mean by bipolar operation. Okay, bipolar operation, it enhances the selection, okay, of the power system. As you see here, there is 3 types of connection: monopolar, bipolar, homopolar. And we here choose for the microgrid, DC microgrid, bipolar link. This means there is no current will pass between the neutral here. So the low voltage DC link in the DC microgrid is simply supported by bipolar operation, like this connection. The second type of the microgrid is the AC microgrid. Generally, the renewable energy sources and the load can form a small isolated AC microgrid or AC system. We can say about it, it's AC microgrid. We can say any village could have its own electricity by this system, AC microgrid, to get various resources of energy like solar, wind, and batteries, and whatever, maybe hydrogen also could be possible one day. And really, it's nice to have this in order to be sustainable village. Typical AC microgrid system interconnected with medium voltage. It will be containing these components. Medium voltage level really very important because you can do it as a factory. Most of the factories are connected to the medium voltage level of the grid, so it will be more economical for them to install this microgrid and connect it directly to the main grid also. So they don't need to install the system and then install also long cables in order to um, reach the low voltage grid, or install additional transformer to transform from medium voltage to low voltage and then make this connection. I hope it's clear. So medium voltage level is really more better in this case. And all this system connected to the PCC, which means the point of common coupling. Here, this means the point of common coupling. Here's a circuit breaker. Solar panels, wind turbines, the storage system are connected to the AC bus through the DC AC converter and maybe the AC AC converter. The same. The AC AC converter and the wind turbine converts, not converts, it transfers the power from the wind turbine to the grid and regulate the voltage level. Generally, the renewable energy sources and the load can form small isolated AC grid, as I told you before, and it will be really very helpful. Maybe you remember in the beginning of the talk, I told you there are two types of the microgrids. They could be connected or not connected to the main grid. Here is the classification more and more details. The coupled AC microgrid is directly connected to the utility grid through transformer, which is placed at the point of common coupling, as you see here. Okay, here is the point of common coupling. We could have here transformer before connecting to the main grid. The decoupled AC microgrid is connected to the AC DC converter first, and then connected to the DC AC converter in order to be linked to the power grid. So let's summarize it. The coupled AC microgrid is directly connected to the grid, but decoupled AC microgrid is connected also, but indirect. Okay, that's why it's called decoupled. Microgrid directly connected to the utility grid is one of the advantages of the AC coupled network. Really, it increases the capacity of the system at all over. We have here really amazing application which we will see now about the Simris project in southern part of Sweden. Really, it's nice application for microgrid. As you see here from Google Maps, um, that's, yeah, that's good. As you see here from the Google Map, the location, it's farm, really brilliant location for a AC microgrid in order to supply the village and maybe supply these farms by energy. Here is another picture, but from your reality, not satellite this time. As you see here, the solar panels and some storage blocks, and here the wind turbine. Also, this system contains a lot of different things, not only the wind turbine, solar energy, and battery. The main assets forming the local energy system, this system called local energy system, it has main 5 parts. The energy management system, okay, in order to really control the delivery of the power into the conventional grid according to limitations within the conventional power quality limits. That's very important to obey these rules of voltage and frequency regulations of the grid in order to be connected to this. Otherwise, you need to be isolated. As I told you before, it's called islanding mode. We will talk about it soon. The second part of this local energy system is the battery energy storage system, BESS. They have around 333 kilowatt hour of the batteries, which operates as a grid forming unit and is in charge of the instantaneous balancing of the microgrid. We will see very soon how it do it really, because mainly we mean about grid forming unit. We mean that it is really setting the certain value of voltage and controlling the system when it is become islanded and isolated from the main grid. Okay, so the battery system or the storage system in general, storage system could be fuel cell, could be general battery banks, anything we could store the energy in it. Number 3 is the secondary substation. Okay, we can call it DER substation. DER means distribution energy resource substation. Distribution energy resource means that we have a lot of different renewable energy connected to the grid. So we call it distributed because everyone has different location, and of course they are energy resources. They could be built next to the existing wind turbine and PV panel, as is located here. Okay, and here from the satellite you can see it. This is the substation and fully equipped by the necessary communication, protection, relays, and control systems and device needed to run the LES, which is the local energy system. Also, the biodiesel backup generator, it has around 480 kilowatt rated power in order to have it like a backup, of course, in any case of fault in the system. So we need to be isolated from the grid because, as we mentioned before, if we are connected to the main grid, we need to follow the regulations of the main grid. Otherwise, we should be isolated from this. In the case of isolation, we need to be fulfilling all the requirements of our customers. That's why we need to have backup generation. Also, we have something like the brain of the system, which is the demand side response, which really steers smart technologies like the heat pumps in the houses, the hot tap water boilers, or the electric vehicles charging stations. Also, they have in this application electric vehicles charging stations in order to have really smart and microgrid in this city. Let's have an overview about the system and what contains. For this pilot project in Simris in Sweden was connected and disconnected from the main grid. You see, it could be connected and also it could be disconnected in some cases. It could be disconnected while being sourced at times solely by the renewable energy coming from the local wind turbine, the PV farm, and the rooftop PV installations of the local households. They have around 150 customers in this system. So the local energy system as a whole is created on top of already existing grid. It has 5 substations, everyone like really, sorry, 7 substations, everyone converting from 10 kilovolt into 0.4 kilovolt. And we have our substation, as we mentioned before, the DER substation, number 3, okay? The voltage of this, it's 10 kilovolt distribution system that forms the local energy system to supply 150 customers. Also, the feed-in point to the local energy system, we mean feed-in point, which is the point of common coupling as we mentioned before. Let's go back here for a second. Here, okay, in this point at the circuit breaker, it means the feed-in point to the local energy system. It will be this substation 20 over 10 kilovolt. It will be also equipped by power breaker, as you see, circuit breaker and voltage and current transformers for measuring, of course, and protection relays. Here is the summary of all the components of this system. We have here central battery, EMS, energy management system, wind turbine, PV plant, the large one, and backup generator for any emergency, and substations. We have 7 substations and 1 substation to connect to the grid. The DSR, the demand side response platform, which is, as I told you, the brain of the system, and heat pumps, water boilers, and also the residential PV and battery on the rooftop of the householders. E-mobility, also we have electric vehicles charging stations, and also we have smart meters. We have platform peer-to-peer in order to visualize all the data instantaneously, and of course the local measurement units. As usual, we need to measure the voltage, the current, the frequency, and others, maybe the active power, reactive power, and so on. And here are the manufacturers or vendor list of it. Let's start to talk about the operation of this system, the pilot project in Simris. Mainly, the energy management system is in charge of the load balancing responsibilities, really. You will see very soon how it operates accordingly to the emergency cases. It's really very amazing. It consists of industrial field proven hardware from this company Incorp located in the BES, you see, the energy management system with the yellow box located here in the DER substation and also located, uh, sorry, it's located here in the primary substation and the DER substation here, DER substation, which contains the renewable energy resources connected here, and also in the battery system. Okay, the EMS, the energy management system, has direct control over the power breaker at the point of common coupling, as we mentioned before, so that it could be really switched off in order to have islanding mode if we are not fulfilling the requirements of the main grid. The RES generation is also controlled by EMS, which has demand the renewable energy sources to be curtailed, which means reduced in such cases if the energy system, the battery energy system, have high state of charge, so we need to control the generation in order to avoid maybe overcharging, which could be harmful for the storage systems. During times of high demand and low generation, the energy management system can demand combustion engine to operate in order to fulfill the needs of the customer, especially in the case of islanding mode. In the islanding mode, we are disconnected from the main grid, so we need to fulfill the requirements of our customers in the first place. And of course, you will have main regulations like specific voltage level, specific frequency level, in order to avoid any harmful effect to the appliances or any devices at homes or fact, not factories, offices also. The energy management system controls the operational mode of the battery system and sets target voltage and target frequency, as we mentioned, especially when we operate at the islanding mode. In Simris project, the energy system is really core element in the local energy system because when islanded, it acts as grid forming unit. It because it sets the voltage amplitude and the frequency amplitude. The PESS selected for the project is really have great characteristics by rated power 800 kilowatts and an energy capacity of 333 kilowatt hour, as we mentioned before, and it includes PCS functions, which really controls the power system, which allow us to have really smooth islanding, as we will see very soon. The PESS includes three key control elements. The battery management system, which is responsible for the state of charge estimation and enforcing the battery system limits. Also, the BCS inverter control, which is responsible for high-speed switching for the power electronics to manage different operating modes. If we wanted to have a mode of islanding or connected mode. Also, the battery system controller, which including the state machine for different operating modes. We mean like state machine, like any scenario such we could have or face, and manage the transition between them. Okay, we have implied in it some scenarios to operate, like we will see very soon. If the solar system is disconnected, what we will do? So they have certain scenario, and if the wind turbine disconnected, the battery could disconnected. What will be do? What will do? So all these scenarios are implied in the controller. Here is the overview of the energy storage system. We have here the battery system by Samsung, around 7 units each. Here have the units and also connected to controlling units. As you see here, the BCS control. It converts here the power from these batteries to the transformer in order to be connected to the grid. And here we see, of course, delta transformer. It's very important, especially when we deal with electronics. It injects a large amount of harmonics. So in this case, we need to have delta connection in both ways in order to avoid any transfer of the third harmonics, which generated by the electronics. In both ways. We don't need any harmonics to come from the grid or come from this electronics, as we see. Let's start to talk deeply about the virtual islanding mode, which helps to smooth the islanding mode. Okay, virtual islanding mode, we can do it in order to be disconnected at any time we want. Okay, we are agreed with the main grid that we will be connected from maybe 8 p.m. during the peak till morning, and that's it. This is our contract. Okay, so anytime else we could be disconnected accordingly to this contract. So we will be really controlling our disconnection, we can say. So in this virtual islanding mode, the energy management system controls the active and reactive power in order to set values, in order to have like zero power or zero reactive power also exchanged over the point of common coupling. Let's go here. At this point, we control the power, active and reactive, in order to make the summary or the equivalent active power and equivalent reactive power to be zero in order to be ready for disconnection. Why? Of course, in order to reduce the spark or any harmful effect to the grid. So the energy management system controls the active and reactive power in order to have no exchange power at the point of common coupling. The PCS controller, which is the controlling system, running at current source inverter mode. Current source inverter mode, which means the inverter is working under constant current and operates as grid following. It follows the energy management system. Balancing could be managed locally with several distributed LES as we said before, the local energy source during the peak loads. All these things could be really helpful, especially like solar panels on the rooftops of the um, householders. They really could be contributing during this mood in order to help for virtual islanding. In this scenario, the LES provides ancillary service to the overlaying grid, but by adapting their power consumption and generation. Of course, the grid could need, we can say, like uh, 50 kilowatt active power, so we could try to fulfill these needs by our resources, the wind and solar, and could be maybe the battery also, or the diesel generator, for example, in order to fulfill all these needs, in order to be virtually islanded at the end. Okay, this of course increases the overall grid hosting capacity, and this keeps the voltage levels within limits. Of course, all of this means something maybe you are familiar with: power quality. It improves the power quality. We have here the second part of this islanding mode. Uh, One of them is virtually, as we mentioned, mentioned virtual islanding mode. We control the power, the reactive and the active, in order to make no exchange at the point of common coupling. And here is the intentional uh, islanding mode. That will be like emergency case. Okay, in this case, the power system controller PCS inverter running in a voltage source inverter mode. Voltage source inverter mode means it will have constant voltage in this case. And it operates as grid forming because it will set, as we mentioned before, it will set the value of the voltage and the value of the frequency, which will be working during the islanding mode. It allows the BESS to seamlessly transition between the grid connected mode to the islanded mode. To physically island the system, the EMS measures the real and reactive power. Of course, we need to measure in the beginning by our voltage and current transformers, and sets the value for the voltage and the frequency targets for the battery energy storage system, such that the real and reactive power are near zero. It looks like the virtual islanding mode as a step number one, and then the system is now ready for islanding. No power exchange. So if we are really starting to switch off the system, we will have no large um, spark or nothing at all. So the energy management system triggers the circuit breaker in order to switch off this, in order to be ready for the islanding mode. The system is really ready, and the battery system doesn't change the operating mode in order to have smooth transition. Okay. The last step is the energy management system updates after islanding mode. Of course, they updates the values of the voltage and the frequency, and maintains constant values. Like you see, this is like agreement at their contract, like 10.7 kilovolt and 50 hertz power, as this will vary along the PESS droop curve. The droop curve is the curve of the frequency, which is changing the active and reactive power. We will see here the effect of some sudden changes. Okay, I hope it's really clear, this graph. It really describes, the blue curve here is the frequency. This is the droop curve, or the frequency. We have mainly constant frequency, which we target 50 hertz, and sometimes it goes up, sometimes it goes down. We will see why. And we have here at the bottom part of this graph the power generated by the different renewable energy resources, like this one, the wind turbine, and this one is the battery energy storage system, and this one with blue is the diesel generator. Um, yeah, I think it's the main thing. And here is the small one. Down here is the load, the customer load. Okay, so let's start with the moment, which is very clear here. Something happened suddenly at this point, at 11:08:30 here at this moment. As we see here, the battery system is disconnected because it has low capacity. Okay, of course, if you have mobile phone and you reach it to the level of like 20% of state of charge, it will give you a notification that it's really harmful to stay at this uh, uh, condition. You need to charge your phone, and it's better, of course, to switch off your phone and charge it in switching off mode. So in this case, of course, the battery also, uh, the energy management system will control it and force the battery to be disconnected, okay, in order to save the batteries from any harmful effects. At this moment, as we see, the frequency increases rapidly, and then will be decreased also by the energy management system to go back again to the 50 hertz. So this frequency really increased because one thing, which is the backup generator. If you still remember this blue curve, which is belonging to the diesel generator, at the same time, we told you that the diesel generator is working as backup. Okay, so we have now emergency case. The battery storage system is disconnected, so we need to connect suddenly, instantaneously, this backup generator. So when we operate this diesel generator, of course, it's a rotating machine. So when it suddenly connected to the grid, it gives really a boost for this frequency to go up, and the energy management system helps the system to restore it back. Okay, I hope it's clear. Now, let's summarize this point. At this moment, the battery is disconnected. It could be really real emergency case happened. Okay. At the same time, why this battery system disconnected? It's disconnected because it reaches to low level of state of charge, and in order to save it from any harmful effect, we need to disconnect it. At the same time, we need to connect the diesel generator as a backup. When we connected it, it started to operate as a rotating machine, so it increases the frequency level, and in order to avoid any over frequency effect, the energy management system controls the frequency to come back to the normal condition. Okay, everything is now clear. And the wind turbine here stayed still really stable till this moment, also dangerous moment. At this moment, we have the battery disconnected and the diesel generator is connected and the wind turbine is connected. Suddenly, the wind turbine is disconnected for somehow. This condition usually happened with the wind turbine when they have low wind speed during certain time. So this wind turbine could be disconnected, okay? And sometimes if they wanted to do a maintenance, let's say, so they need to lock the rotor, so it will be disconnected. At such cases, we need to be flexible, of course, and have flexible system. That's why it's really smart and microgrid. So in such cases of disconnecting the wind turbine, we will connect at the same time the battery, which is charged a little bit. Okay. At this time, really, it becomes really compensating this. So the wind turbine is tripped and the battery energy storage system is restored and allow the frequency to reduce along here the frequency curve because we lost rotating machine. Here, as you see in this first case, we added a rotating machine, which is the diesel generator, so the frequency increased steeply. And also here we lost rotating machine, which is the wind turbine. So the frequency reduced very much, like you see, and the energy management system also restored the frequency back to the 50 hertz. At this moment, as you see here, small notch, it came from the inertia of the system because at this moment we have sudden drop in the frequency. So the diesel generator as a rotating machine also connected to the grid. It reacts like action and reaction. The action was losing rotating machine frequency drop. So this diesel generator has a reaction for this and increases slightly the power generation in order to compensate this loss of frequency. But of course, the energy management system helps to restore the frequency. So I hope it's clear now, the two cases. First case I described twice. Here, let's summarize. In these two cases, we have emergency situations. In the first one, we lost the battery system. And the second one, we lost the wind turbine. In every case, we have scenario. All these scenarios are implied and we put it in the control system in order to act as we want. In the following figures, we will see at these moments, there were in SEMRE's project, they were testing it on the 12th of April 2018. The system was islanded from 8 a.m., 8 morning to 8 p.m. And we will see the effect of this islanding mood, okay? As you can see here, the effect of this intentional, the graph here to the left, is the intentional islanding mood, okay? And to the right is the normal operation. Of course, these measurements come from the frequency meters. So as you see here, from 8 a.m. till 8 p.m., there is like a constant frequency, yeah, comparing to the same time while we are connected to the grid. So we see really the effect of this islanding mode. It increases and enhancing the power quality of the grid. Of course, we mean the grid of the customers, our customers, the 150 customers. And by enhancing the power quality of the customers, of course, uh, we keep these applications safe. Their laptops, their devices are safe when we have good power quality in the system. And here also we have this voltage profile from 8 a.m. till 8 p.m. It seems constant comparing to the same period while we are grid connected. So it's really obvious that islanding mode is more beneficial for the frequency profile and the voltage profile, which also translated to better power quality. The last thing we need to mention now is really the brain of the system, which is uh, the DSR, really the demand side response platform, which have really connection between really the the microgrid controller, the platform peer-to-peer, and the smart meters. As we know, every element in the system should be connected with a smart meter in order to collect live data, in order to take the right decision. And here is the PV and battery systems, heat pumps, hot water boilers, electric vehicles charger station. All of this connected to the DSR platform in order to take some decisions. Now we are talking about one of the important decisions related to the electric vehicles. The DSR platform is able to send periodic steering signals to the electric vehicle supply equipment via the backend. Backend, of course, we mean the servers and so on, limiting the amount of energy at the charging stations to provide over time. So at any time, we have here electric vehicles to be connected to the grid, and we wanted to charge these electric vehicles. So in case we have no enough energy for these electric vehicles to be charged, so we could control the amount of energy which supplied to the charging station. And in this case, we can say if we have large amount of energy, so we can charge our electric vehicle battery to the full. But if we have limitations of energy at our system, so we could maximum charge our battery to 80%, maybe to 60%, to 50%, something like this. Okay, so this SR controls this something. Okay, I hope all this system is clear, and really we would have three main conclusions from this: that we believe that the local energy system could become an important and powerful opportunity for the energy industry, because really it helps very much, as you see, to improve the power quality, and the local energy systems could guarantee cost-effective integration of the renewable energy sources. This will create amazing local energy communities. We will have really uh, the future, really, like we can say everyone could have electric vehicle and charge it at home, and this home has its own um, renewable energy resources like solar panels on the rooftop, or also energy storage system by batteries or fuel cells. So this is what we mean with local energy communities. So final thing is the local energy communities will support the transition towards a European energy system and combines the sustainability and security, which is really very important point. Security, you can't be connected and have this all um, we can say sometimes wired connection or wireless connection, and you can control all these meters, and you can control the substation, the DER substation, and suddenly someone hacked the system and could island your system and switch off some circuit breakers. It will be really chaos. So it's a combination of sustainability by connecting the renewable energy resources to the grid, and security, and of course IoT. That's a very important topic also connected to this topic. And really it's very important to have vital role from the citizens, or we can say the householders, who can really have their own systems of generation and storage. And in this case, they will be really contributing to improve the main and the whole power quality of the system, which is in return helps them to live better and have more quality energy and more power, actually. And we could remember also one of the slogans of the PES, more power to the future. So this is our main goal, really, to have more power to the future in order to avoid more conflicts in the world. As you see, a lot of conflicts in the world because of resources like energy. So if we have really different ways of energy, so we could avoid a lot of conflicts in this world. We hope. So finally, this is the reference of my presentation. This is in the IEEE PES magazine. There are two main magazines of the PES. The IEEE PES magazine, with the same name, and the IEEE Electrification magazine, in contribution with our sister societies like Industrial Application Society and Power Electronics Society. So there is a topic here talking about microgrids field trials in Sweden, and also there were very nice and beneficial for informative book about integrated renewable energy sources with drop control techniques based on microgrid operation. So you can download this version of the magazine for free, and you could also get a lot of material from the PES Resource Center. You can check it here. As a PES member, you can download free material, and also you could request credits. That's very important for your account. Thank you very much for your time, and I hope it's really helpful information for you, and I wish you have a nice day. Thank you very much. Any questions?
Thank you, Saif. We have now a question from Shirinti. She asked, in this first case study, can the battery system be used for feedback as well? And why a separate biodiesel generator for backup?
Please again. Uh,
In this first
comment.
case study,
Comments.
can the
Yeah,
battery
I
system be
didn't hear.
used for backup
In
as
this,
well? And why?
the first case, can't the
And why a
battery
separate
system be used?
biodiesel generator?
Yes, yes, exactly. Yeah. So that's a nice question. It is according to this system. Of course, they have some elements, and they wanted to test the effect of every action. That's the main thing. Of course, battery in this system, they give it a rule of forming, like a forming unit of this system. Mainly, it has the rule of setting the value of the, or keeping the value of voltage. And of course, mainly the battery system is always connected, okay, in order to store the energy which is generated by the renewable energy resources. So it can't be as a backup because it's really main uh, element, vital element, okay, in this system. But they could have some storage elements like at the householders. They could have also separated batteries. They could be a backup in this case. So the diesel generator really more uh, used as a backup in general cases, actually, not only in this system. We have some countries which have shortage in electricity. Sometimes the main grid is cut off, so they have like backup generator in order to keep the power supply. So this is the main concept. Okay, I hope it's clear now. Uh, so let's summarize the answer. In this system, they make the battery system, which is the battery energy storage system, as a grid forming element, okay, in order to have stable voltage during the islanding mode. And the diesel generator, it is as acts as backup. As you see, of course, in the second case, when we lost this wind turbine, the battery system come back again. Okay, so it acts like also backup, we can say. But mainly, all these situations, they made it like scenarios for emergency. If we face the low state of a charge, what we will do? We will operate the backup generator, of course. And in the second case, if we lost the wind turbine, what we will do? We will connect the battery system. So this is the main point. So generally, you could form your own system. In this case, you could make your battery system as a backup, and also uh, this generator as a backup. But you need to choose one of them. Of course, in the first case, we could consider uh, the diesel generator as a backup, and in the second scenario, we could consider the battery as a backup. Okay, I hope it's clear, because it's very flexible. You could consider any of this as a backup. Thank you for your question. Anything else?
Thank you, Mr. Mohammed. I would like to thank you again for your fruitful webinar and for your time, especially for your time. Thank you everyone for joining us today to celebrate POS Day. Happy POS Day, and don't forget to subscribe to our POS Young Professional channel and also to follow us on our social media channels.
Happy PS Day.
Thank you, and have a nice Happy PS Day. Thank you.